Okay, so this week we start talking about exponential and logarithmic functions. I just want to start with a review of the terminology dealing with exponents. So anytime we have a power, which is an exponent base combination, a base being the number that's repeated, and the exponent being the number that tells you how many times you repeatedly multiply the base, these together are called a power. When we were in Algebra 1, we first learned about the laws of exponents. So what we do if we multiply powers with the same base, if we raise a power to another power, if we divide powers with the same base, or if we raise a quotient to a power, or what to do if we have a negative exponent, for example. This is a picture of the graph of an exponential function. The base in this case is 2. So the base could be anything. An exponential function is defined by a variable in the exponent. So we could raise any number to any power, but the basic shape of every exponential function will be this kind of curve, this L shape, and we'll talk more today about why that is the case. And then the logarithm is the inverse of an exponential function. If you remember, inverses graphically are reflections across the diagonal line y equals x. Hopefully we remember that from Unit 1. Inverses undo each other. So we can think about that in a few different ways. If we were to compose one function into the inverse of its function, they would reduce to x or cancel each other out. It is the same thing as swapping the x and the y values, which is what creates the reflection across the line y equals x. To find the inverse, we simply switch our x and our y values and then resolve for y. And so logarithms and exponential functions are examples of inverse functions. They're also known as transcendental functions. Other transcendental functions that we've studied this year are the trig functions, sine, cosine, tangent, cosecant, secant, and cotangent. And they're called transcendental just because they can't be expressed as an algebraic or a polynomial function. So they can't be expressed just with numbers and variables. So a logarithmic function, like I said, is the reflection of the exponential function that we saw here as long as they have the same base. And we'll talk more about what these mean because you haven't seen a ton of logarithms. You touched on them a little bit in Algebra 2, but you haven't studied them in great detail. So we'll get to that in a future video, but for right now we're just going to focus on exponentials. But just please keep in mind that they are inverses of one another, so they go hand in hand. Okay, so now specifically, any exponential function is any base written to some power that is our variable. So our exponent is the variable in this case. One of the most common bases that we're going to see with exponential functions is the letter e. E is it's a constant. Please don't confuse it for being a variable because it's a letter. Kind of like pi, it represents this irrational decimal that goes on forever. And the reason that we use it a lot is because it has a lot of practical applications in these different areas. We're going to see it a lot with the word problems that we study in this unit. Okay, so let's see what the problems are going to look like that you might have to do. So basically, an exponential function is anything right where we have a variable in the exponent. We can simplify them by plugging in a number for that variable and then just putting that into our calculator. Exactly the way we see it. So I'll show you in Desmos how that's done. So for the problem that we had on our paper, f of x equals 2 to the x, where x equals negative 3.1, we would just plug in that negative 3.1 where we saw an x and then put that into our calculator. So we could type the 2 and then we use our exponent button and then we type in our new exponent. And it gives us our decimal. We're going to get a lot of decimals in this unit. And the directions say to round to the nearest thousandth. So that's how we would do all of these problems up here. We're basically just plugging in a number for x. Okay, a big part of this unit is going to be graphing different types of exponential functions, which means we're also going to need to restudy our transformation rules, but we'll get to that in a second. So here are two basic parent functions of an exponential, f of x equals 2 to the x that I've done in yellow, and I can create the graph by plugging in different values for x and getting my y and plotting those points. So when I plug 0 in for x, 2 to the 0 becomes 1. 2 to the first power is 2, 2 to the second power is 4. And remember, negative exponents, they don't make your base negative. What they do is they actually take the reciprocal. So 2 to the negative 1 becomes 1/2, and 2 to the negative 2 becomes 1/4. So when I plot those points, that's what creates this kind of curvy line. And one thing that I'd like to point out about the graph is that it doesn't matter how negative I make my exponent. I'm always going to have some number that approaches 0 but never gets to 0. So all exponential functions have a horizontal asymptote. F of x equals 4 to the x is kind of done in this pinkish purpley color. Same thing, except my base is now 4. It makes the same kind of curve shape, but you can see that it's a little bit steeper because that base of 4 is making the graph grow bigger. So instead of multiplying by 2 every time, I'm multiplying by 4 every time. So each number gets 4 times bigger. So it makes it steeper, and it also bottoms out more quickly. Okay. So this is pretty much the same thing, except we have a negative in our exponent. And we're going to see that when we create a table, just like we did before, it basically just flips our graph horizontally, because now all of the x's that I plugged in now become negative because of that negative exponent, and all the negative numbers that I plugged in become positive. So it kind of flip-flops my values, and so it creates this horizontal reflection. And if we remember, all horizontal transformations occur in the exponent, or in other words, they're grouped with the x. And because our x happens to be in the exponent now, anything that happens horizontally will happen in the exponent. And don't forget that when we're shifting or when we're dilating, any horizontal transformations are always going to be opposite from what they see, which leads us to our next example. So if we take the parent function of 3 to the x, I've graphed that, if you can see, in black here. So I have a point at 0, 1, because 3 to the 0 power is 1. At 1, 3, because 3 to the first power is 3. If I could fit it, it would be at 2, 9, because 3 to the second power is 9. And if I go the other way, 3 to the negative 1 power is 1/3. And again, I start to bottom out, creating that horizontal asymptote again. That's my parent function. So in this case, I'm shifting to the left 1 because the plus 1 is inside the exponent. Here I'm shifting down 2 because the minus 2 is outside the exponent. Here I'm reflecting vertically because the negative is outside the exponent, and here I'm reflecting horizontally just like in the previous example because my negative is inside the exponent. And you can see how that affected the parent function to the right here on the graph. So all those transformation rules are the same. We're just applying it now to the exponential graphs. Okay, and we're going to focus in the next example on specifically that base of e. And again, we can do this all on our calculator. If you come over here to Desmos, for example, you don't have an e button, but if you go to your regular letter keyboard and then type the letter e and then go back, you can raise that to any power, and Desmos automatically knows that you mean the base of the natural letter e. Or I should say the natural number e. So if we did e to the negative 2 power, it gives us a decimal of 0.135 if we round it. And so that's how we're going to do all of these problems as well. And now we're going to take a look at how we see exponential graphs, or functions in the real world. A very common one is in banking. And this is where you're going to want to refer to that formula sheet that I posted in the teacher course materials section. So this is what I'm referring to. Here are all the formulas that we're going to use in this unit. So banking is a big one. Like I said, calculating compound interest, continuously compounding interest, half-life, population growth or population decay. And actually it's kind of fitting that we do the exponential unit right now because the spread of coronavirus is an example of an exponential function in the real world. Here are all the meanings of your variables if you need them. And these formulas don't have to be memorized. I would always give them to you. Okay, so let's go back to our problems. So in example 6, this is an example of compounding interest that's compounding annually. So our n is going to be 1. N is the number of times that we compound interest in a year. So if we're compounding it every year, then we're compounding it once in a year. 9,000 is your principal amount. 2.5% is your rate. We just have to convert it to a decimal. We talked about the n value, and the t is for 5 years in this case. So we just plug it into the formula that we're given and put that into your calculator exactly the way you see it. And you should get 10,182.67 once you round it. This is a second compound interest problem, although this one compounds sorry, where does it say? Oh, I'm sorry. We're compounding it quarterly, which means 4 times a year. So our n is equal to 4. And here we're going to do continuously compounding interest. So that's going to use our other formula. So here we use our compound interest formula in the same way that we did here. The only difference is that our n is 4. Here we use our continuously compounding interest. And because it's constantly compounding, there is no n. There's no number of times that we compound it. So our formula doesn't have an n. The e in this formula is that constant that we talked about in the notes previously. So we plug this into the calculator, 12,000 e to the 0.03 times 4, and we should get $13,529.96. Radioactive decay. In this case, they're actually giving us the formula they want to use for the half-life of strontium, which has a half-life of 29 years. So the initial mass, or the initial amount of strontium, meaning the amount that we have when the time is 0, is what we would do by plugging 0 in for our t, or our length of time. And when we do that, it makes our whole exponent 0, and anything to the 0 power is 1, so strontium starts with 10 grams. After 80 years, though, it will decay at this rate. Now we're plugging 80 into our formula. And when we simplify that, we round it and we get about 1.478 grams. So after 80 years, starting with 10 grams, we'll end up with 1.478 grams. Okay, and then population growth is represented, in this case for fruit flies, by this equation. So to find the initial number of fruit flies that we have in our population, again, that's at time 0. So we just plug 0 in for t into that formula. And so again, it makes our exponent 0. Anything to the 0 power is 1. So we start with 20 flies. But after 72 hours, we plug 72 in for t. We get about 173 flies. So this one I rounded to the nearest whole number because it wouldn't make sense to have a decimal number of fruit flies. So the rounding is going to depend on your problem. For the most part, you're going to want to go to 3 decimal places, but again, it depends on the problem. Okay, so that's it. Email me if you have any questions and take a look at the associated problems for day 1. You don't have to do all of them. They're just all of the different types of practice problems that you could see. And I miss you guys. I'll see you soon. Bye.